Welcome everyone. I'm excited to kick off our presentation with today's topic, linear equations in two variables. In this session, we'll explore what these equations are, how they work, and why they're important. We'll look at their forms, how to solve them, and what their graphs look like. So, let's dive in and discover the fundamentals of linear equations together. Let's take a look at slide 2, which outlines the contents of our presentation. We start with an introduction to the topic, setting the stage for our discussion. Then, we move into understanding what a single linear equation is and how it forms the foundation for solving more complex problems. Next, we explore systems of two linear equations, which are essentially two equations considered together, and how to identify if they have a common solution. This leads us into the condition for a common solution, including the continuation of that concept. We then delve into algebraic solutions for these systems, showing how to solve them step by step. The cross-multiplication method comes into play as an efficient technique for solving such systems, and we'll see how to apply it through various examples. Throughout the presentation, we also examine different types of problems, including example problems that help reinforce the methods and concepts we've discussed. Overall, these points are interconnected, building from basic concepts to more advanced problem-solving techniques, all aimed at enhancing your understanding of linear equations and their solutions. Let's take a closer look at the general form of a linear equation in two variables, which is written as a x plus b y plus c equals 0. Here, a, b, and c are real numbers, and both a and b are not 0. This is important because it ensures that the equation actually represents a line. Now, when we have specific values for a, b, and c, we can find the corresponding x and y that satisfy this equation. Essentially, we're looking for the solutions, those pairs of x and y that make the equation true. This form is quite fundamental because it allows us to analyze and graph lines easily, and it connects directly to the overall theme of understanding linear relationships between two variables. Remember, the key is that for any given a, b, and c, the solutions form a straight line in the coordinate plane. Let's take a closer look at the graph of equation 1, which is shown in figure 1. What we see here is that all the points x, y that satisfy this equation actually lie on a straight line. For example, the point 0, 2 satisfies the equation and is clearly on that line. This illustrates an important idea. Infinitely many pairs of x and y values can satisfy this equation, meaning there's an endless number of solutions. The key takeaway is that a linear equation like this represents a straight line, and every solution corresponds to a point on that line. This concept is fundamental because it helps us visualize how solutions to linear equations behave in the coordinate plane. Now, let's explore how a linear equation in two variables can be visualized. Geometrically, such an equation represents a straight line in the Cartesian plane. This means that every solution to the equation corresponds to a point on that line. Many relationships we encounter in real life can be expressed using a linear algebraic equation in two variables. For example, consider the equation displayed here, which is equation 1. 2y equals 3x plus 4. When you graph this, you'll see it forms a straight line, like the one shown in figure 1. To make this more relatable, imagine the cost of bananas and oranges. Let's say the cost of a banana is rupees, and the cost of an orange is y rupees. The relationship between their costs can be described by an equation. The total cost of 2 oranges is 4 rupees more than the cost of 3 bananas. This is a perfect everyday example of a single linear equation, illustrating how such relationships are everywhere around us. Understanding how to interpret and graph these equations helps us grasp the connections between different variables in a simple, visual way. Let's look at this example. 2 times 3x minus 2y plus 4 equals 0. Now, what's important here is understanding how we can manipulate equations without changing their fundamental meaning. For instance, multiplying or dividing both sides of an equation by the same number doesn't alter the equation itself. So, if we multiply both sides by a number or divide, the equality still holds true. Here, we see an example where we add 10 to both sides of the equation. 3x minus 2y plus 4 plus 10 equals 0 plus 10. Again, the key point is that adding or subtracting the same number on both sides keeps the equation balanced. These operations are part of what we call properties of equations, which are essential tools for solving and simplifying linear equations. Remember, whether you're multiplying, dividing, adding, or subtracting, doing the same thing to both sides preserves the equality. This understanding helps us manipulate equations confidently and accurately, which is at the core of solving linear equations efficiently. Let's take a closer look at this graph, which represents the two linear equations we're working with. The first equation, x plus 2y plus 4 equals 0, is shown here as equation 2. The second, 3x minus 2y plus 4 equals 0, is equation 1. These two lines are an example of a system of two linear equations in x and y. By graphing both equations, we can visually see how they interact, whether they intersect at a point, run parallel, or perhaps coincide. The key idea here is that solving a system like this often involves finding the point or points where these lines meet, which is called the solution to the system. Understanding these graphs is fundamental because it helps us visualize the relationships between the equations, making it easier to grasp concepts like substitution, elimination, or graphing methods for solving systems. This connects directly to our overall theme of understanding how systems of equations work and how we can interpret their solutions both algebraically and graphically. Let's look at this example where minus 2, minus 1 is a common solution to both linear equations. When we substitute x equals minus 2 and y equals into the first equation, x plus 2y plus 4 equals 0, we get plus 2 times minus 1 plus 4, which simplifies to 0. Similarly, for the second equation, 3x minus 2y plus 4 equals 0. Substituting the same values gives 3 times minus 2 times minus 1 plus 4, which also simplifies to 0. This shows that the point minus 2, minus 1 satisfies both equations simultaneously. And as a result, the two straight lines represented by these equations intersect exactly at this point. Remember, both of these equations describe straight lines, and their intersection point is where they cross on the graph. This example highlights a key concept in systems of two linear equations. Their solution, or solutions, if they exist, correspond to the points where the lines intersect. Let's take a closer look at Figure 3. As you can see, when lines are parallel, there is no common solution. That means they do not intersect at any point. Both lines in this graph are parallel, which confirms that they do not meet. Now the equations shown here are equation 2, which is 4x plus 6y equals 24, and equation 1, which is 2x plus 3y equals 6. Notice how these lines are graphed based on these equations. This leads us to an important point. When two lines are parallel, they have the same slope but different intercepts, and because of that, they lack a common solution. In other words, there's no point that satisfies both equations at once. This idea connects directly to our overall theme of understanding solutions to systems of equations. Recognizing when lines are parallel helps us quickly determine when a system has no solution, which is a key concept in solving these problems. In Figure 4, we see that the two lines are either the same line or they overlap perfectly, which means they are coincident. This results in infinitely many solutions because every point on one line is also on the other. Both lines are parallel, as indicated in the graph, which tells us something important about their slopes. We have the equations 7x plus 7y equals 21 and x plus y equals 3. Notice that these two equations represent the same line, just expressed differently. This is a key concept because when two equations are essentially the same, they have infinitely many solutions. Understanding this helps us recognize when systems of equations are dependent, meaning they describe the same line, and thus have infinitely many solutions. It's an important building block as we explore the conditions for solutions in linear systems. Now, let's discuss the key points about the solutions to two linear equations represented by straight lines. First, If the two lines are actually the same or coincident, then we have infinitely many solutions. This is because every point on one line is also on the other, so they overlap completely. Next, if the lines are parallel but not coincident, then there is no common solution at all, meaning they never intersect. Finally, when the lines intersect at a single point, that point is the unique solution to both equations. These conditions help us understand the nature of solutions based on the position of the lines, which ties back to the overall theme of analyzing solutions of linear equations visually through their graphical representation. Let's go through how the solution 1 satisfies both equations 1 and 2. Since it checks out, we can be confident that our solution is correct. Now, looking at the second equation, 2 minus y equals 3, we see that solving for y gives us y equals -1. Next, to find x, we substitute x equals 1 into equation 1, which is 2x plus 3 equals 5. Doing that, we find that x equals 1. Notice how in step 2, y is eliminated, and now we can focus solely on solving for using equation 4. Equation 4 is 4x minus 2x minus 3 equals 5. By substituting y from equation 3, y equals 2x minus 3, we connect the two equations. To solve for y from equation 1, treating as a constant, we look at 4x minus y equals 5, which is equation 2. And similarly, 2x minus y equals 3 is equation 1. This approach demonstrates the method of elimination by substitution. It's a powerful technique for solving systems of linear equations, especially when the variables can be isolated easily. Overall, this algebraic method helps us find exact solutions efficiently, and understanding this process is key to mastering systems of equations in algebra. Let's look at how the point 1 satisfies both equations, confirming it as a correct solution. When we substitute x equals 6 into the first equation, we get 3 times 6, which equals 18. This matches the right side, so the first condition holds. Similarly, substituting y equals 1 into the second equation, we see that 205 times 1 plus 205 equals 0, confirming that 1 is indeed a solution. Next, to find the value of y, we substitute y equals 1 into the second equation, and it simplifies to 0, solidifying our solution. Moving on, when we subtract equation 4 from equation 3, we derive a new equation, 33x minus 220y minus 22 equals 0, which is our simplified form. Recall that equations 3 and 4 are derived from earlier equations, which we got by multiplying the original equations by certain factors. Specifically, multiplying the first original equation by 3 gives us 3x minus 20y minus 2 equals 0, and multiplying the second by 11 yields 11x minus 5, y plus 61 equals 0. Now, these two equations form a system of linear equations. The method we're focusing on here is the method of elimination by equating coefficients. By manipulating these equations, multiplying to align coefficients, we can eliminate one variable and solve for the other efficiently. This approach simplifies solving systems of equations, and it's a fundamental algebraic technique we'll explore further. It's all about adjusting coefficients so that when we subtract or add the equations, one variable cancels out, leaving us with an equation in a single variable. This technique is powerful for solving linear systems systematically. Let's look at the key points here. First, notice the expressions involving a 1, a 2, b1, b2, c1, and c2. These are the coefficients from our system of equations. When we eliminate one variable, either y or x, we get these determinants. A 1b2, a 2b1 multiplied by the variable, equal to a combination of the constants c1, c2, and the coefficients. This determinant plays a crucial role in solving the system. Specifically, by eliminating y, we derive the equation, a 1b2, a 2b1, equals b1c2, b2c1. This is a key step because it simplifies our problem to solving for x directly, provided that the determinant isn't 0. Similarly, when we eliminate x, we get a 1b2, a 2b1, y equals c1 a 2, c2 a 1. This shows us how the elimination process works symmetrically for both variables. Now, let's look at how substitution helps us find y in terms of x from the second equation. We isolate y as y equals c1 b1 plus a1x, assuming b1 isn't 0, which is given. This substitution method is a powerful tool because it reduces the system to a single variable, making the problem more manageable. Furthermore, to eliminate y completely, we substitute this expression for y back into our first equation, which is a 2 plus b2y plus c2 equals 0. Remember, this is valid as long as a 2 and b2 are not 0, to avoid division issues. Finally, these steps, using determinants, substitution, and elimination, are fundamental in solving systems of linear equations. They connect directly to the overarching theme of understanding how to find solutions efficiently, especially when dealing with multiple equations and variables. Let's take a closer look at this system of equations where x equals k and y equals L, both set to 1. Now, we can rewrite these equations using the formulas shown here. The key point is that y equals this fraction, which involves the determinants of the coefficients, specifically the numerator being c1 times a 2 minus c2 times a 1, all over a 1 times b2 minus a 2 times b1. Similarly, for x, we have b1c2 minus b2c1 in the numerator, divided by the same denominator. It's important to notice that this denominator, a 1b2 minus a 2b1, must not be 0. If it were 0, the equations wouldn't be solvable using this method, because it would mean the equations are either dependent or inconsistent. This approach is part of the method of solving systems called cross-multiplication. It provides a straightforward way to find the solutions for x and y when the system is consistent and the denominator isn't 0. In essence, the most critical concept here is understanding how the determinants of the coefficients determine the solvability and the solutions of the system. This method ties into the broader theme of solving linear systems efficiently, especially when dealing with two equations and two variables. Hence, equations 1 and 2 are essentially the same, which means there are infinitely many solutions. Now, consider the second equation, a 2 plus b2y plus c2 equals 0. We can write this as k times the same expression, so k times a 2 plus b2y plus c2 equals 0. Expanding that, we get k a 2 plus k b2y plus k c2 equals 0. If we set c1 equal to k c2, then equation 1 transforms to a 1 equals k a 2 and b1 equals k b2. Now, when the determinant, b2 minus a 2 b1 equals 0, we see that we cannot divide by that quantity to find unique solutions for x and y. This condition, where the determinant equals 0, indicates that the equations are dependent, or essentially the same line, which ties back into the idea of infinitely many solutions. Now, moving on to the next section, which is case 2, we are going to explore how to solve such systems using cross-multiplication, a very useful method when dealing with these dependent equations. This is not true, hence no solution exists. Or c1 equals k times c2. Or k times negative c2 plus c1 equals 0. K times a 2 plus k times b2y plus c1 equals 0. Then, equation 1 becomes, if c1 is not equal to k times c2, we encounter a contradiction that indicates the system has no solution. This is a key point because it highlights when the system of equations is inconsistent. Understanding these conditions helps us determine whether a solution exists or not. In the context of solving systems of linear equations, this is where cross-multiplication can be a useful tool to analyze the relationships between the coefficients. So, in summary, recognizing when no solution exists is crucial for efficiently solving these systems. Let's walk through this example problem step by step. We start with the two equations, x plus y equals 7 and 2x minus y equals 5. Our goal is to find the values of x and y that satisfy both equations simultaneously. To do this, we'll use the elimination method, which involves eliminating one variable to solve for the other. Notice that if we add the two equations together, the y terms will cancel out because one is positive and the other negative. So adding the equations, x plus y plus 2xy equals 7 plus 5. This simplifies to x plus 2x plus y minus y equals 12, which reduces to 3x equals 12. Dividing both sides by 3, we get equals 4. Now, to find y, we substitute x equals 4 back into one of the original equations. Let's use plus y equals 7. Substituting, we have 4 plus y equals 7. Subtract 4 from both sides, and y equals 3. So, the solution to this system is equals 4 and y equals 3. This example highlights how elimination helps us efficiently solve systems of equations by removing one variable at a time. Now, looking at this slide, we have two variables, x equals a and y equals. The key idea here is to understand how these equations relate to each other and how we can manipulate them to find solutions. First, notice that when we add the two equations, we get x plus y equals a plus b. This is a straightforward addition. Next, if we multiply the first equation by b, we transform it into an expression involving both and y multiplied by b, which helps us prepare for elimination. Similarly, multiplying the second equation allows us to set up the system for elimination by aligning the coefficients. The goal here is to eliminate one variable to solve for the other. By doing so, we can find the values of x and y more easily. This approach, using multiplication to align coefficients, is a fundamental technique in solving systems of equations efficiently. It's important because it illustrates how algebraic manipulation can simplify complex systems into manageable steps, ultimately leading us to the solution. So by applying the cross-multiplication rule, we find that x equals 6 and y equals 11. This leads us to the equation x plus y equals 17. We can rewrite that as x plus y minus 17 equals 0. Similarly, for the second equation, 12x minus 5y equals 17, which we can also rewrite as 12x minus 5y minus 17 equals 0. Now, the key point here is that these two equations are set to 0, which makes solving them more straightforward once we have the relationships. The overall solution involves solving these equations simultaneously, using the cross-multiplication method again, and that's how we find the values of x and y. In this example, the goal is to reinforce how cross-multiplication simplifies solving systems of equations, especially when dealing with ratios or proportions, connecting this back to our broader theme of solving linear systems efficiently. Moving to the problem itself, notice how the table of values helps us see the relationships between x and y clearly, which supports our understanding of how these equations work together.